is when we speak to customers who have either developed their own methods, used startups or partners, or even collaborated with us, it's very promising, but there are still some challenges to the size of the cases, the data sets in a way, challenges in maturing the technology to fully realistic scenarios. And there is still work to be done to fully understand how to get the best out of these methods in terms of the accuracy. So I'd say, yes, people are definitely showing very promising early results, but there is also a lot of secrecy. Yeah, not so much public information out. And that's why we are trying to be as transparent as possible through dataset creation, through publishing papers, to try and help people to hopefully see in a transparent way, you know, what's the good things and the bad things. And so one of the things that we've done is publish a paper at a conference. It's called the SAE conference. It's one of the main automotive conferences. In fact, my colleague yesterday was there presenting the paper in Detroit. And this actually is already out of date. This is always the case of academic work, because you have to submit it 6 months ago or a year ago. Yep. It's already actually out of date. So in a way, part of me goes, oh, I really would like to update this paper, but you know, that's not the way it works in academia. And this paper basically is just the start that hopefully shows the promise. And our central philosophy with this is the cost saving and time saving, and to explain why people are interested in these methods. So we set about doing that, and what we did is we split the paper and the work essentially into different use cases. It's all focused, as the title says, on road vehicle aerodynamics, but actually almost all of the things we show here have the same promise if it's a wind turbine, if it's an aircraft, if it's a building. We don't think any of these ML methods are a replacement for existing CFD methods. We still think there's plenty of work and room to create more accurate, faster with latest GPUs and codes, but that there is most definitely a use case for what we're calling the lower fidelity part. So where most customers, they do high fidelity, right? But these simulations may take days to run at quite a lot of cost. So they have a sort of lower fidelity bit. That's the bit where we see ML potentially being an important tool. So, for example, you may have an error of 5% or 7%, but it's okay because it's just in the conceptual design phase. You just want to get a quick indication of whether it's better or not. Stuff that you would go, you know what? Okay, that's been useful. Now I'm going to, whatever I think is my best design or my best 10 designs, maybe that I'll now run through my high fidelity. So it's more giving you an additional tool to explore a bigger design space. So really, it's not a net cost saving probably. You're probably still going to run your normal number of simulations. And it's long been a goal of more real-time or very fast ways of getting insights. It is definitely a way to help, productivity, essentially.
But more to the point, productivity for some of the rarest humans on Earth.
Oh, yeah. You probably spend more per hour on the salary cost than you do on their use of a license per hour. So they are more expensive. So what we did, just very briefly to summarize, so we got like this sort of car. So we built a data set. Now, this was actually with a very small data set. It was only actually about 15 different cars. And surprisingly, the results are still reasonably good. But so we created these data sets, different geometries that all run with the same airflow speed. It's a test of geometry prediction. And what we focused on were 3 particular areas, and a fourth being a Gen AI piece. So the first one is a drag. So what you see in this graph here is predicted actual. It's a very standard sort of ML graph. What was very interesting is when you look at the actual test data, the error is less than 2 or 3%. So that means that once you train the model and you test it on unseen variants of this geometry, the drag that you get out is within 2 or 3% error, which is actually, pretty good from an engineering point of view. So for this to actually train, it was only about 20 minutes. The paper goes into the full details of the particular method, so I won't go into it now. But we give a dollar cost based on the actual Amazon EC2 instance that was used. And so it's about $1 to train. And then the inference, it's about 5 seconds, and the cost is 0.004. And just to give you an idea that the actual CFD simulations, were hours on, let's say, 1,000 cores. So at a cost of over $100, let's say. So now this is a small data set. So if you have a larger data set, it's going to cost you more. But you can still see why the training versus inference for just the KPI is incredibly cost effective and fast. So that's the first data point that goes, okay, this may not be completely accurate, but this was like, okay, now I see why there's some potential. But this is just lift and drag, right? Mm-hmm. Engineers want to see things. They want to understand that's the whole point of computational fluid dynamics in a way. Mm-hmm. So the next stage was, let's try and predict some images. So when you do a CFD simulation, you can output images of the flow, let's say in the X direction behind the car. It's very common to do this sort of thing, particularly in the automotive and motorsport. Mm-hmm. So we said, now, for all those trained data sets, we've got pictures of the flow behind, like the velocity or the pressure. Let's try and predict those pictures. So we did that. And what you see with that is just here, where on the left you have the actual CFD, and on the right you have what the ML predicted. They're not perfect, and I'll be transparent that there are examples we've seen in current work where it's worse than this, and we've seen examples where it's a bit better than this. But the point is, it can give you broadly the correct flow topology, so what it looks like, what an engineer can interpret, and to give you an idea of the sort of timing and cost. Now it's a bit more because you're actually dealing with more data, more images. So it was, a couple of hours, although actually our most recent work, it's quite a lot faster than that. Maybe now $10, $12, but the inference is still about 5 seconds for, almost nothing. So that's another example. You get a bit more detail, it takes you a bit longer to train, but your inference is still basically real time and your cost is minuscule. So this, again, was to give us some indication of, okay, there is quite a strong potential for these methods. The final one is, can you try and predict the full 3D volume? So that means you take in as trained data the entire case. Now, this was actually for a motorbike. And can you get out at inference the 3D volume? So in this figure, basically what we're showing is at the top is what we call the ground truth. It's the CFD. It's coming from OpenFOAM. It's the pressure on the top left and the velocity on the top right. Probably the velocity makes the most sense. So red is high speed, blue is low speed. So as the flow goes over the bike, the flow separates, and that's what causes the drag. That's the blue bit. That's what slows the motorbike down. That's why you need an engine to push through it. The middle is what the machine learning gives you. So on the left, pressure, on the right, velocity. And on the bottom, it's the standard, is the error. So what's the difference between the two? Now,
right. And obviously, the darker on that error one at the bottom, the darker the red, the more clearly the greater the error. So how do you evaluate this? Is this okay? Is this not bad? What's the...
Yeah, I mean, as a scientist, I still want it to be better.
Sure.
But from a conceptual design point of view, it certainly shows the promise that by doing this, you can get broadly, okay, the flow separates off that wheel at the back. You can see the blue bit coming. That's the flow separation. The flow separates off the top of the rider, which is that sort of blue blob in the middle. But like with any ML, it's all about, if we'd have given it more data, if we'd have changed some of the hyperparameters, we probably could have improved this. But it was more to give a sense of, even with a relatively quick study using open methods like this UNet method, that the potential is there to be able to do it. And again, what we wanted to give a sense of was the computational cost to do it. I think I mentioned before, when we look at the other methods, I gave the numbers of, let's say, 20 minutes to train, it was $1 for the simplest KPI. We then go to 2D slices, we're talking $10-ish, so maybe a couple of hours to train.
Yep.
The third one, by the way, is a sort of a nuance. It's similar to be able to predict its KPI, but goes into more detail. But I'll skip just to the last one because that's the contrast. Is now this takes quite a lot longer to train, so maybe 3 times more. So 8, 9 hours, 10 hours.
Right.
But for this example, that's still only about $36, and the inference is still near real time. Now, I do want to make clear that particularly this last example is using a relatively small mesh, and it's a large data set, so it's about 500 cases, but the actual case itself was like an OpenFOAM tutorial case. So I do want to call out that probably to do this for real life, this cost would be quite a lot higher.
Neil, we've got customers who are spending millions of dollars a month training their large language models. Training a model on, say, I don't know, if you're a motorcycle manufacturer, you've got probably a decade worth of simulations. It might cost you a considerable amount of money to train a model, right? But even at that point, you're talking thousands or tens of thousands of dollars to train a model. But the impact of it is you're going to get a model that's particularly suited to your motorcycle designs. It's going to give you some ability to do some really rapid iterations on speculative design ideas, and at least get you close to an outcome, right? So that you can then go and start the CFD modeling.